welcome back to Mathematical Statistics. Today we're going to finish up our intro to hypothesis testing. Remember, we're coming back later to do more general and more interesting hypothesis testing. We just did a little bit, scratch the surface right now so that we can start thinking about the language of hypothesis testing so that when we do the more interesting stuff later, we're not bogged down with trying to understand terminology. After today, we're going to do estimation. We're going to do method of moments estimation, maximum likelihood estimation, and we're going to find the UMVU, the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. What this means is if we have a target parameter theta that we want to estimate, and you come up with an unbiased estimator, and I do, and they do, and they do, and everyone in the known universe does, if I have the UMVU, I know that I have the best in terms of the smallest possible variance out of anyone, and no one can do any better. So it is just that cool. And we're getting there. But we want to finish up hypothesis testing. Okay, so let's get into it. We were in the middle of an example that I want to sort of restart here. We had x1 through xn. They were IID from a normal distribution with mean mu and variance sigma squared. And both of these parameters are unknown. And we are doing a hypothesis test for the mean. And the ones we've done so far, we've always known sigma squared. So another thing that has changed in this example is we have moved on to a composite looking alternative hypothesis. So our null hypothesis is going to be that mu is some fixed number, and our alternative was that mu was greater than that fixed number. The two hypotheses should really cover the entire parameter space, and mu goes from minus infinity to infinity. So this doesn't really cover it, but it is a simplification. We are more general than we were last time when we had just like a mu equals mu naught versus a mu equals mu1 that was even more simplified. So we're working our way towards the entire parameter space. But remember, these are the only two conclusions, and this one, the null hypothesis, is assumed to be true unless we have a lot of evidence in the data for this, and there will be no concluding that mu is less than this fixed mu naught. So this second or alternative hypothesis is composite because if it was true, we don't know the exact mean and therefore we don't know the exact distribution, so it's not a simple hypothesis. But actually, the null hypothesis is also technically composite because if it was true, we know the exact mean, but we don't know sigma squared, so we still don't know exactly what distribution the data comes from. So usually simple looks like an equal sign and composite anything else, but technically that's not quite true. But this is our first time looking at an inequality. And again, we don't know sigma squared. So I did give you the statistic to base this on. I'm just going to jump right in with our steps. Step one for hypothesis testing is going to be to choose a statistic to work with. You can think of this as being an estimator of the unknown parameter mu or a statistic which could be an estimator for the unknown mu, but maybe not looking like it because anything could be an estimator. And so here at this point in the course, I'm giving you the statistic. We're going to use X bar. Since we're trying to find a hypothesis test concerning the mean of a distribution, the sample mean is probably a good thing to look at. Okay, so step two is going to be to write down the form of the test. So remember, we're assuming that mu equals mu naught, and we're looking for evidence that mu is greater than mu naught. And how would that be reflected in our statistic X bar? If the true mean is really above mu naught, and the mu naught is not that important, if it's larger than mu naught, but the key word is larger, then we want to reject the null hypothesis and go with the alternative. So the form of the test should be something like this. Reject the null hypothesis in favor of the alternative if so evidence for mu being large is going to be that our sample mean is going to be large. So if x bar is greater than c for some constant c to be determined. Could you make this rule instead, let's say x bar greater than mu naught plus a constant c, which would actually be a different constant? Yes, you could. But we're just going to do it this way. It's going to be a little simpler and cleaner and easier. But today, I really want to focus on us doing hypothesis tests for various parameters and various distributions. I want to get away from normality. And you can set these things up many ways. So I'm going to stick with this as my rejection rule. Step 3 is going to be to find C. And here's where you use alpha, which is going to be a given size or level of significance of the test. I didn't completely restate the whole problem. We're doing a hypothesis test here based on x bar. We're trying to derive a size or level of significance alpha test for these hypotheses. So an alpha has been given, and that's how you find C. We have a simple looking null hypothesis with an equal sign. Alpha was the probability of making a type 1 error. This is the probability that you reject the null hypothesis when you shouldn't have because it's true. So rejection for us means that x bar is greater than c. That's our rejection rule. And when it's true means that the mean is really mu naught. We started with normal random variables, and this x bar has a normal distribution because it's a linear combination of normals. The next step in computing a probability involving the normal distribution would be to standardize x bar to write it as a standard normal, so we can look up probabilities in a z-table or use like z critical value notation. But standardizing x bar means that you would have to look at x bar minus mu over sigma over the square root of n, and we don't know sigma for this problem, so it's not going to be useful for our test in the end to involve sigma. If the sample size is large, we could use the sample variance and say it's a good enough approximation of sigma squared, the true variance. But here I'm not assuming the sample size is necessarily large. So what do? If we have a normal distribution and we don't know sigma squared and we're using the sample variance s squared, that's where a t-distribution comes in. So I'm going to standardize my x bar using the sample variance, and let's do it on both sides here. I'm going to take x bar symbolically over here minus the mean over the standard deviation, which is capital S, which is the square root of our sample variance, over the square root of n. And on the right side, I'm going to do it with the specific numbers. So I do know specifically in this statement that mu equals mu naught, so that's what I'm going to subtract. The standard deviation is whatever it is. Presumably, you have this so-called data in front of you, and you can take it and you can compute the sample variance, which computationally might be easier to compute like this. But if we have the data, we can compute that, and therefore we can use this sort of expression in these probability statements. So I'm going to finish this, capital S over the square root of n, when mu equals mu naught. Okay, so if the true mean mu is mu naught, then this has been standardized. It is normal. It is recentered and rescaled, which is still normal, but it hasn't been properly scaled using the true standard deviation sigma. Therefore, the thing I just circled has a t-distribution with n minus 1 degrees of freedom. And this thing over here is just a number. So I am going to give this a name. Usually at this point, I write a Z because it's a standard normal, but now I'm going to write a capital T or any letter you want greater than C minus mu naught over S over the square root of n. And I'm done with the information that mu equals mu naught. I just need to say that this T here has a T distribution with n minus 1 degrees of freedom. Okay, this whole thing is equal to alpha, and the T distribution is a bell curve that we cannot integrate very easily in closed form. We can't like write down a CDF in closed form. So this is one of those distributions where we would use a tabulated critical value, and we will leave our answer in terms of a symbolic critical value. Our goal is, remember, to find C. Right now, I have a T distribution with n minus 1 degrees of freedom. I have a random variable from that distribution greater than a number with probability alpha. So if this is the T n minus 1 curve, I want to find a number that I will be above with probability alpha. And the name of this critical value here is T sub alpha, comma, n minus 1 in our notation. You might be following a different notation from another resource, but this is the notation we are using to denote the number that cuts off area alpha in the upper tail for the Tn minus 1 distribution. So in other words, the probability that T is greater than T alpha comma n minus 1 is alpha. But we have this entire thing in here instead of this. So this entire thing needs to equal that critical value. So we need C minus mu naught over S over the square root of n, and that is a capital S. It's maybe not that clear, equal to this T critical value with n minus 1 degrees of freedom. And you solve for C and you get mu naught plus T sub alpha n minus 1 S over the square root of n. So we're finished with step 3. We have found C. And step 4 is to just bring it all together with your conclusion. So we're going to reject the null hypothesis in favor of the alternative if x bar is greater than this C we just found, which is mu naught plus T alpha n minus 1 S over the square root of n. And we're done. This is a test of size or level of significance alpha for this set of hypotheses for a normal distribution when both mu and sigma squared is unknown. It's not the only test. For example, we can use a different statistic. We could replace this, as I was saying, with something like x bar is greater than mu naught plus a different constant. Let me give it a different letter, like a D, and then find D. There are many different things we can do. At the beginning of this class, I hinted that the UMVU is coming. Now, that's an estimation thing where you can find the best estimator in all the land. And there is something coming up later called a uniformly most powerful hypothesis test, which is going to give you the best hypothesis test in terms of whatever that means. We do need to talk about that. So that will choose the statistic for you. It will choose the form of this rejection rule for you. Right now, we're just sort of picking something and formulating a rejection rule, either like this or like this, and getting a conclusion. And your neighbor might actually find a different hypothesis test than you, and it could still be 100% correct. Both by design would have size or level of significance alpha, but if you and your neighbor were using different tests and they both had size alpha, they would maybe differ in terms of beta, the probability of a type 2 error. You'll notice that the fact that the alternative hypothesis has this inequality as opposed to the equalities we've been looking at hasn't come into this problem at all. It comes in when looking at a type 2 error. And yeah, we won't get this in closed form because of the t-distribution, but let's consider finding the type 2. So this is the same, I'm continuing the example, the type 2 error for this test. Beta is probability of making a type 2 error. Did I say we were finding a type 2 error? No, we're finding the probability of making a type 2 error. And that is the case where the null hypothesis was false, but you failed to reject it. So let me write that down. This is the probability you fail to reject the null hypothesis when you should because it's false. This is our rejection rule. So when are we going to fail to reject the null hypothesis? We're going to fail to reject it if our x bar is actually less than or equal to mu naught plus t sub alpha comma n minus 1 capital S over the square root of n. When it's false means when mu is greater than mu naught, because that was the alternative hypothesis here. That was the not HO sort of thing here. When you want to compute a probability involving a normal, you want to standardize it by subtracting its mean and dividing by its standard deviation. And we have a problem because there are many possible means here. So what value of mu should I subtract? Let's imagine this is actually like mu greater than 3. Should I subtract, when standardizing this, should I subtract mu equals 3 or mu equals 3.2 or mu equals 100? There's lots of possibilities there, and I don't know how to proceed. And that's okay, because this definition is just wrong when you have a composite hypothesis. The same thing's going to happen when we switch to making this an inequality. We're going to have to slightly vary our definition of alpha. So I'm going to leave this type 2 error probability behind because, as stated, we can't do this. So let's now talk about the alpha and the beta when you have composite, null, and alternative hypotheses. So alpha and beta for composite hypotheses. Maybe one of them is composite or both of them. Before this, don't write this down because I'm going to, well, if you do, leave a space. This was the probability of making a type 1 error. And now what we want to do is control not only that error, but kind of the worst case scenario, the highest probability error. So we're going to look at a maximum here. And that maximum, this is going to be, in our previous example, a function of mu, or in general theta, and we're going to max over all mu in, so I'm going to put is an element of like that, in the null hypothesis. Because this is the probability you reject the null hypothesis when you shouldn't because it's true. And so we want to look at all of the mu's in that null hypothesis, all of the possible mu's when the null hypothesis is true, and look at the maximum error we could make and try to control that. The beta, this will make more sense when I do examples because I really haven't set up the notation for this very well, but is going to be the maximum probability of making a type 2 error. And this maximum is going to be taken over all mu's in the alternative hypothesis. Kind of. So it is conventional for our null hypothesis to always include the the equal sign in the case that we're doing hypotheses with inequalities. Remember, we will eventually get to crazy hypotheses where the null hypothesis might be that the sine of theta is greater than 1/2, something like that. So not just a simple inequality. But if you have inequalities like mu less than or equal to mu naught versus mu is greater than mu naught, it is conventional to put the equal part of that inequality in the null hypothesis. There's a problem then when looking at this definition for beta, because we don't have an equality here. I guess this isn't going to make sense until you see what actually happens. But before we do an example, I just want to talk about supremums really quickly. Those maximums should technically be supremum. So a supremum for a set of numbers is a least upper bound. And all this is a maximum, even when the maximum is not in the interval. So if you consider the collection of all x's for which x is between 0 and 1 inclusive, and you want to find the supremum, that is the largest x in that set, and it's going to be 1. If you want to look at, let me do a maximum here. If you want to look at the maximum x in this set of x's, that is also 1. Suppose you want to look at the maximum x in the open interval as x goes from 0 to 1, but not including the endpoints. In this case, there is no maximum. Because if you want the largest x in this set, it's not 1 because 1 is not in there. So it's 0.999999999, but whatever it is, there's something above it and below 1. So this maximum doesn't exist, but we say that the supremum of the x's in this set is 1. It is, again, the maximum when the maximum doesn't quite make it in there. So let's talk about this least upper bound terminology. If you imagine like a number line, 0 and 1, and maybe we're looking at this set of numbers, the supremum is an upper bound to this interval. So this is, get color here, this is an open interval. Here at 1.7 or 3.9, I don't know, my scale's not so right here, is an upper bound for everything in that open interval. So is this, so is this, so is this. And the smallest of the upper bounds before you start moving under things that are in that interval is right here at 1. So that's why the supremum is 1. It is the upper bound on this interval that is as small as it can possibly be. And that's, a mathematical thing, but informally, it's the maximum when the maximum isn't quite in there. So in hypothesis testing, you'll always see the alpha and beta defined in terms of maxes, but really they should be supremums. So you'll see what I mean. We're going to do many examples, but if you find yourself computing one of these maximums over a set and the maximum is not attained in that set, you can grab that endpoint. It's really a supremum. So these really, instead of max for max, should say sup for sup. Let's do a whole new example from scratch, a whole new distribution, and composite versus composite. Suppose I have x1 through xn, IID, exponential with rate lambda. I want to derive a hypothesis test of size alpha, also level of significance alpha, for the null hypothesis that lambda is less than or equal to lambda naught versus the alternative that lambda is greater than lambda naught. Now, the parameter space, the lambdas, do have to be greater than 0, so presumably this is something positive, and really what this hypothesis is saying is this, but we usually don't bother to write that. It's just a given that we are, restricted by our parameter space. And I did promise you that I would give you the statistic here. We've worked with this distribution and estimating the parameter with two statistics. One was the minimum of the distribution, which does not have a lot of information, right? Because if you are sampling from this exponential distribution, the minimum is just sort of down by 0, no matter what lambda is. And then we've used X bar, the sample mean, which has more information about lambda because the mean of this distribution is 1 over lambda, so there's kind of a relationship there. But as you know, we use the minimum a lot as an easier example, just to, to follow the steps and make sure we can do things. So that's what I'm going to do here. I'm going to say based on the minimum x1 in parentheses, which is the minimum of x1 through xn, just because. Okay. Step 1 is to choose a statistic, and this has been done. We are using the minimum. Eventually, you'll have to actually do step 1, and I like to just write it there every time. Step 2 is to come up with the form of the test. Or another way to say this would be the sort of shape or structure of the rejection region. We are going to look at the statistic that is the minimum, and we want to look at our hypotheses. So this one is assumed to be true. And if we see evidence for this, we're going to dump the null hypothesis and go with the alternative. So how would you see evidence for this in the data? If lambda gets larger, what happens to the data? There are two ways to think about this. One is to look at the PDF, which is lambda e to the minus lambda x. So it starts at lambda and goes down exponentially. So if someone else is starting with a higher lambda, it has to come down faster in order for the total area under each PDF to be 1. It's not going to stay above the other PDF. And so the green PDF I drew has more area or probability down towards 0. It's going to tend to produce smaller numbers overall. Another way to see that a larger lambda will produce smaller numbers in the data is to note that the mean for any one of these, their IID, so anyone, is 1 over lambda. So if lambda is large, the numbers coming out on average are going to be smaller. All right, so the form of the test. We look at our statistic and we say, if this alternative is true, what happens to this statistic? Honestly, the minimum, especially if you have a large sample, is just going to be stuck down by 0. It's not going to show you very much, but all numbers in this distribution are going to tend to be smaller when this is true. The mean, the x bar, is going to be smaller. An individual x is going to tend to be smaller. The maximum x in your sample is going to tend to be smaller, and the minimum is going to tend to be smaller. So all these kinds of things, not every possible statistic, but these kinds of things which give you a sense of location of things. If lambda is large, then the x bar is going to turn out to be small. The max and the min are going to turn out to be small. You can imagine, again, with that picture, like random sampling from the white distribution, my original, and then random sampling from the green distribution, yeah, you can get something higher, but overall, everything's going to tend to be, it doesn't even look like it at all. Those green ones, swap those colors. Those green ones are supposed to look smaller. But yeah, the form of the test. So here we go. We're going to reject the null hypothesis in favor of the alternative. I don't need to write this part because my null and alternative hypothesis cover the entire parameter space. So it's not like mu or lambda equals lambda naught versus lambda is greater than lambda naught. And I see evidence for lambda actually being less than lambda naught, but we don't go there. It's not so important to put this in favor of part if the minimum is small in the sense that it's below C or some constant C to be determined. So the direction here was completely determined by the direction of the alternative hypothesis. But here's an example of a greater than producing a less than. So you don't just want to, not think about what you're doing. If a larger parameter will produce a smaller value of your statistic, then seeing your statistic below a number is going to be your evidence for the parameter being larger. So we are done with step 2. We have the form of the test. On some of your homework problems, I only ask you for the form of the test, which is basically half of a hypothesis test, and you could stop there, so you don't have to find the C. But here, we want to derive the test. No one said anything about finding the form of the test. So we are at step 3, which is to find C. And you find C using alpha. So alpha is the maximum probability of making a type 1 error. There's a maximum there because the null hypothesis is composite, but technically you could always put a maximum there. If your null hypothesis looked like lambda equals lambda naught, then you are taking a maximum over all the lambdas in the null hypothesis, which is looking at a function of lambda, and instead of maximizing it over some region, you're maximizing it over a single point. And there's only one point there, and that is the maximum and the minimum. And so we didn't actually change the definition. This max definition will work across the board, even if you have simple hypotheses. I didn't write the lambda stuff there. I'm going to hold off until I'm a little more specific. The next line. So this is going to be the probability, actually one more line, that we reject the null hypothesis when we shouldn't because it's true. So rejection means that our minimum is going to be less than some C, and then it's true is when the parameter is lambda, and that is a variable. But over in the max statement, we're going to look at all lambdas less than or equal to lambda naught. Now, a shorthand way to say this is going to be to replace the when the parameter is lambda with just a semicolon lambda. Occasionally, people will use a vertical line. I don't like to use that for reasons, but if you use it, I'll understand what you mean. Okay, so how do we maximize this? We really need to know how this is a function of lambda. So let's compute this probability and hopefully get a function of lambda and then look at its maximum over the lambdas that are less than or equal to lambda naught. If the parameter is lambda, put an arrow this way. This means that x1 through xn are IID exponential with rate lambda. And this means that the minimum is exponential with rate n lambda. We've seen that result a few times. But if not, you know how to find probabilities for minimums. You already have it in the form of like a CDF, and you could try to rewrite this probability as it relates to the individual x's, and you could do this from scratch. But I know that the CDF for an exponential with rate lambda is 1 minus e to the minus lambda x. If you don't do the integral, it's not bad. So here I don't have an exponential rate lambda, I have an exponential rate n lambda, and that means that this probability, which is a less than probability, or less than or equal to, because the equal sign doesn't matter in the continuous case. So um, let me write this over here, sorry. The probability that the minimum is less than or equal to c is going to be 1 minus e to the minus n lambda c. C goes in for x and n lambda goes in for lambda. And then if this is a strict inequality, it doesn't matter because it's a continuous random variable. So there's zero probability of actually landing on C. So in other words, going back to the left side, this is 1 minus e to the minus n lambda c. So there's a function of lambda, and we can think of maximizing it over all the lambdas less than or equal to lambda naught. You might graph this function, um, but I don't think we even need to do that. Look at this as a function of lambda. As lambda gets large, this part of the exponent gets large. And that means that if you put the negative in front of it, this gets small. Or you know what, better than that, let's look at this as 1 minus 1 over e to the positive n lambda c. As lambda gets large, this exponent gets large, which means e to the exponent gets large, which means this fraction gets small, which means 1 minus something that's getting smaller and smaller is actually getting larger and larger. So what I'm trying to say is this is an increasing function of lambda. So without thinking about how it really actually looks, I'm just going to draw a, I don't want it to look linear, but I'm just going to draw, an increasing function of lambda. So if we want to maximize this probability over this region, that maximum is going to occur at that endpoint where lambda equals lambda naught. In other words, going back to the left, this function is maximized when you plug in lambda equals lambda naught. In some cases, to do this maximization here, you would have to use calculus, but a lot of the times you're going to see an increasing or decreasing function where the maximum over a region is going to occur at an endpoint of the region. Okay, so we are in step 3, finding C, and we're almost there. At the very beginning, we had an alpha. So now we have, just to recap, alpha equals 1 minus e to the minus n lambda naught c, and we want to solve for C. So this is e to the minus n lambda naught c equals 1 minus alpha. If I take the log on both sides, I get this, and then I divide. So c equals the negative 1 over n lambda naught times the log of 1 minus alpha. As a quick check, this makes sense. We're talking about a rejection rule that looks like we're going to reject if the minimum is below some c, and everything is positive for the exponential distribution. So like the minimum is never going to be below a negative number. But this is okay because log looks like this. It goes through, intercepts the x-axis at 1. And so it's negative when you plug in numbers between 0 and 1, and alpha being a probability between 0 and 1. 1 minus alpha is between 0 and 1, unless you took alpha to be 0, which would be silly, or 1, which would also be silly. So this is negative. And so with the negative out front, everything is nice and positive. Okay, step 4 is going to be to write down your conclusion, to bring it on home. So we're going to reject the null hypothesis in favor of the alternative if this minimum, what did we say, is less than C. And we just figured out what C is. So is less than -1 over n lambda naught, the log of 1 minus alpha. That's it. That's our rejection rule. And this is a test of size or level of significance alpha for testing this null hypothesis versus this alternative. So the alternative gave us the kind of direction or form of the test, and the composite null hypothesis changed how we compute alpha by a little bit. Remember, you can use this max definition no matter what, because if you are, don't write this down because I'm not finished with this problem, but if you had, or this is like a marginal note, if you had lambda equals lambda naught, and you found yourself computing alpha as the maximum probability that the minimum is less than C when the parameter is lambda, but lambda could only equal lambda naught. Here you have a function and it is increasing in lambda, but increasing, decreasing, I don't care because there's only one lambda we're looking at, and that's right here. So if you ignore the rest of the function and just look at that point, of those points, what lambda gives you the maximum? It's lambda naught. It gives you the maximum and the minimum, gives you the average value of this function. So maximizing over a single point is possible. You just plug in the point, and that's why using this maximum or supremum definition will take care of all of your cases. You don't need the simple definition anymore for alpha and beta. Okay, so now let's find beta. Beta is supposed to be the maximum probability of making a type 2 error. So this is the maximum probability that we fail to reject the null hypothesis when we should because it's false. So we are rejecting the null hypothesis when this happens. So we're going to fail to reject when the minimum is greater than or equal to -1 over n lambda naught log 1 minus alpha. And then the when it's false really literally translates to when lambda is greater than lambda naught. But I'm going to tie up the false with the maximum. So I'm going to say when the parameter is lambda, and then we're going to look at all lambda greater than lambda naught. So this is H1, and this is when the null hypothesis is false. That's the region we should be looking at. Okay, I do know that this has an exponential distribution. When the parameter is lambda, this has an exponential distribution with rate n times lambda. We know the CDF for that is 1 minus e to the minus n lambda x. Instead of plugging in an x, I'm plugging this in. And instead of the CDF, we're actually looking at the upper tail probability. So you do not need to write this next line, but I'm just going to write it to be as clean as possible here. Because this is continuous, this is strict, you can change this to a strict inequality. And then this is 1 minus the probability that the minimum is less than or equal to blah, blah, blah. And this is 1 minus e to the minus n lambda, and then whatever. So go through it in slow motion if you need to, but I claim that this probability is 1 minus 1 minus, so we end up with e to the negative n lambda times, this question mark is really this whole thing. Negative 1 over n lambda naught log 1 minus alpha. Before maximizing this, let's clean it up. I could cancel the negatives, I could cancel the n's. And if you want to take advantage of the e and the log, let me write this just first. This is e to the positive lambda over lambda naught log of 1 minus alpha. If we had e to a log, we could cancel them. But remember, we can pull this up as an exponent on the 1 minus alpha. So this is the max over lambda greater than lambda naught e to the log of 1 minus alpha to the lambda over lambda naught, which is the maximum lambda greater than lambda naught of 1 minus alpha lambda over lambda naught. Now, alpha is a probability. It's between 0 and 1. And let's just assume it's not 0 or 1 because that would be weird for a type 1 error. So this is strictly between 0 and 1. And when you take powers of that, larger and larger powers, you get smaller and smaller numbers. So if I want to maximize this as a function of lambda, I want lambda to be as small as possible. In other words, this entire thing here is a decreasing function of lambda. And so we've got some sort of decreasing function of lambda, and we want to maximize it over some region that looks like this. This is actually where you need a supremum, because if this is an open interval, then the maximum is like not in the interval. So it's okay if you keep writing max. Technically, this is a sup or supremum, and you get that when you plug in lambda equals lambda naught. So we get cancellation, we get 1 minus alpha. So our beta is 1 minus alpha. Remember, that is not always true. We've already seen examples where it's not true, and we talked about how alpha and beta are errors that occur in different universes. One assumes the null hypothesis is true, in which case you could reject or fail to reject, and you have a 1 minus relationship there for probability. But in general, beta is not 1 minus alpha. But it happens a lot in these sorts of inequality setups where the maximums that we compute are on the boundary between the null hypothesis and the alternative hypothesis. Okay. I want to define one more thing and then do one more example, and then we'll call it good on hypothesis testing for now. I want to talk about something known as a power function for a hypothesis test. This is different than the power of the test. The power of the test is 1 minus beta, in this case alpha. And we want high power. That's a good thing because that is the probability you reject the null hypothesis when you should reject the null hypothesis, because it's the complement of the probability you fail to reject the null hypothesis when you should reject it. Power and power functions are related, but they are not the same thing. They're not the same thing. They're not. Every year, everyone confuses these, and it must be something I'm doing. So let me say this again. Power function is different from the power of the test. So in this last example, Um, let's find the power function for this test. Our notation is going to be, well, there is not a standard here. I like to use a gamma. It's going to be a function, forget the last example, sorry, we'll go back to that. It's going to be a function of the parameter theta, and this is the probability you reject the null hypothesis when the parameter is theta. And theta could be from the null hypothesis, it could be from the alternative hypothesis, it could be anywhere in the parameter space. So this, yeah, it's a variable. It's a variable. This is a function of theta. The power of the test is a number. The power function is a function of theta. And so let's look at this in the last example. Give the power function of the test that we just derived. So I'm going to call it lowercase gamma. A lot of people use, well, this is really all over the place. I've seen a capital K used a lot and like a capital kappa, but there's no standard notation here. Instead of theta, I'm going to use our specific parameter, lambda. This is a variable that takes on values from 0 to infinity, everything in the parameter space. This is going to be the probability we reject the null hypothesis when the parameter is lambda, and it's going to be changing as lambda changes. Now, in our last example, our rejection rule was that the minimum is less than the negative of 1 over n lambda naught times the log of 1 minus alpha when the parameter is lambda. I'm going to put this with a different color. This is fine if you have an equal sign because it's the same, because this is a continuous random variable. And therefore, we are looking once again at the CDF for an exponential random variable with rate n lambda. So this is 1 minus e to the minus n lambda, right? Because the parameter is lambda. So that means that this is exponential with rate n lambda. And we're evaluating this CDF at minus 1 over n lambda naught log 1 minus alpha. Looks very similar to what we just did. And it is. We're not maximizing it over the alternative hypothesis region. If you simplify this, you get 1 minus alpha to the lambda over lambda naught. What does this look like as a function of lambda? If you sketch this, it is something that is increasing in lambda, and it's kind of concave down like this. And this is some function representing the probability you reject the null hypothesis, not when it's true, not when it's false, just when you reject it as a function of lambda. So it is increasing. It does not have to be increasing. This is not a CDF. But on the x-axis, let's look at the regions where the null hypothesis is true and the alternative is true. So if this is 0 and this is like a fixed lambda naught that's given in this problem, this is the null hypothesis is true region, and this is the null hypothesis is false region. So if the null hypothesis is false, you definitely want to reject this. This is a probability, so it is going to max out at 1. And it's going to keep increasing. It's going to approach y equals 1 asymptotically. So what do we see here? We want to reject the null hypothesis with high probability if we should reject it, if it's false. So a power function for a good test should be up high in the region where the null hypothesis is false, and then lower in the region where the null hypothesis is true. Where is alpha on this graph? Alpha is the maximum over all lambda less than or equal to lambda naught of the probability you reject the null hypothesis when it's true, but I'm not writing the null hypothesis parameters here. That's taken care of over here. So this should be the maximum over all lambda less than or equal to lambda naught of the power function, which is maximizing this function that I've sketched over this region, and that is right here. So the scale is probably way off here, but this is where alpha is. What is the point of a power function? We're not really going to need it until later, but I've talked about making a better test, a best test. What if you redid this entire example, but instead of making a test based on the minimum for the exponential distribution, you make a test based on x bar, and you give your result in terms of chi-squared critical values? Both tests by design will have size or level of significance alpha. That is, both tests will have the same probability of making a type 1 error, but they will differ in the type 2 error region where the null hypothesis is false. The way you can determine that one test is better than another test is to compare two power functions. So if we have like another test for the last example, the exponential distribution, based on the sample mean x bar, we'll come up with a completely different rejection rule. And we can make a power function for this test as well. Now, this one isn't going to be nice and closed form because it's going to involve some chi-squared things. But you can imagine like one power function and a second power function. That is the power function associated with the test based on the minimum and the power function associated with the test based on x bar. I am going to draw a couple of power functions here, and I'm going to ignore the fact that we actually have a shape for this function. If this is my lambda axis, and here is lambda naught, and here is where the null hypothesis is true, and here's where the null hypothesis is false, we want this power function, so I won't put a 1 or a 2 up here because I'm going to sketch them both. We want it to be, it's the probability we reject the null hypothesis. We don't want to reject it when the null hypothesis is true. So we want both the functions to be very small over here and very large, as close to 1 as we can get over here. So a power function might look like this. It does not have to be increasing. I'm going to draw another example in a moment. In this picture, the alpha is the maximum probability of rejecting the null hypothesis when it's true. This power function is the probability you reject the null hypothesis when the parameter is lambda. So if you look at the lambdas for which the null hypothesis is true, in this picture, you're looking over here, the maximum occurs right here. So this would be alpha. What if I had a second test, let me color code this, and computed its power function? If my second test is better, the probability we reject would be even smaller here where we should not reject the null hypothesis because this is the region where the null hypothesis is true. So you want the probability of rejecting to be small, but you want the maximum probability of rejecting over that interval to be alpha. And so a power function for a better test would start lower, would go through that point, and end higher. My green power function is a better test. So later, when we want to come up with the best test in all the land, we're going to try to optimize a power function and try to get something that looks kind of like it's 0 here and 1 here. We're not going to get there, but we're going to try to get a really extreme version of this curve. So again, a power function can be used to compare two tests, and power functions can look like anything. They're not increasing or decreasing. They can be wiggly and weird. And so if you have a third test with a power function that looks like this, then I can't really compare that test to the other tests because I can say that, like, for example, here it is highest of all three. So for these lambdas, the test corresponding to the pink power function is the best test. But we don't know what lambda is, or we wouldn't be doing any hypothesis testing. So if I have a power function that says this one is better for some lambdas and not better for others, but we don't know lambda, it's not helpful. So again, if you draw two power functions, you may not be able to compare the tests. But I could with the original two that I drew here, because I can say, you know what, for any lambda, when the null hypothesis is true, one of these functions is always lower than the other, and it's always greater than the other when the null hypothesis is false. Okay, so before we go, real quick, I just want to talk about power function shapes. They do not have to be increasing or non-decreasing. They are not CDFs. They are involving probabilities, so the y values are between 0 and 1, but they could be some very strange shapes. And it totally depends on, number one, what your hypotheses look like, and number two, whether or not you have a good test. So as an example, if we're testing like that a mean is equal to something versus a mean is not equal to something, what would the power function of a good test look like? The power function is going to be a function of mu, and it is defined to be the probability you reject the null hypothesis when the parameter is mu. So here is my mu axis, and I guess I probably want to show some negative mu's here if this is a normal distribution. So let me put down a fixed mu naught and then a top here at height 1. If you have a decent test, because you can make a really bad test, if you have a decent test, this is supposed to be the probability you reject the null hypothesis, and you should not reject it when it's true. This is the only point where the null hypothesis is true. So you would like the probability of rejecting the null hypothesis to be small there and to be large everywhere else. So if you have a decent test here, your power function will probably look something like this. Because for these hypotheses, this right here is the only place where the null hypothesis is true. And then over here and here, the null hypothesis is false. So you want the probability of rejecting it to be high when you should reject it because it's false, and low where you should not reject it because it's true. So there is a perfectly reasonable power function. So you can see it's not an increasing kind of thing. Also, if the hypotheses are inequalities going the other way, so greater than or equal to versus less than, then now if you put down a mu naught, this is the region where the null hypothesis is true, and this is the region where the null hypothesis is false. And so if you had a good test, you would want something really small here and really large here, and maybe this height would be alpha, this height would be 1, and this height would be alpha, the maximum probability of rejecting over that region where the null hypothesis is true. So you could get something like the U shape before, you can get something decreasing like this, and you could even get, a really bizarre shape. Um, but sometimes looking at two power functions, you'll be able to tell which test is better, and sometimes they just won't be comparable. We're going to get a lot of practice with that towards the end of the class when we really get into hypothesis testing. But one more time, it is not a CDF, but it is a probability. So it's always between 0 and 1. It doesn't have to be increasing or decreasing. It could be almost anything as long as it's a function taking values on the parameter space and spitting out values between 0 and 1. Real quick, if I came up with a second test for these hypotheses and it was better, then it would have a smaller probability of rejecting the null hypothesis when the null hypothesis is true and you don't want to reject it, and it would be larger over here. So maybe something like this. Well, something like that. So that's how you could compare two tests. But again, you could have really wild things that you can't really tell which is better just by looking at the power functions. But for everything in this course, I think you are going to be able to compare power functions. So just remember the y-axis here is the probability you reject, and you want that to be high, close to 1, when the null hypothesis is not true, and you want it to be low, close to 0, when the null hypothesis is true. Okay, now I'm really out of time. So next time we are going to start estimation. We're going to start method of moments estimation. It's going to be our first formal method of estimation. Actually, I want to fit in one more example of a hypothesis test and a power function, but then we're definitely going to be estimating on our way towards the UMVU, the uniformly minimum variance unbiased estimator, the best estimator in all the land. Next time on mathematical statistics.